So for the most part, excluding trigonometry and logarithms and exponents, at the end of this chapter, you should be able to graph in excruciating detail any function. If it turns out that the graph of a function looks like that, and that is an example that we would do in this chapter, then you should be able to do things to the equation of the function and come up with that sketch. And by the way, if you did know the equation to that function and you put it into your graphing calculator kind of has a panic attack and it doesn't quite do a good job of sketching the graph. So this is what we're looking at. And today in this first lesson, we're just going to review some very fundamentals of sketching functions, very basic ideas, and then we're also going to talk about symmetry of functions. So to begin with here for a review, when you find y-intercepts, you let x equal 0 and you solve for y. When you find x-intercepts, you let y equal 0 and solve for x. Those are two ideas we learned all the way back in grade 10, even with linear functions, but it's true for any function. And then in this unit, in the last chapter, we learned that if you want to find out locations of local extrema, which means max min, then you determine the derivative and you do a first derivative chart. So a little while ago, I had shown you the picture of a graph, this graph. If I gave you the equation of this function, right now you have the ability to identify this point, and this point, because those are all x-intercepts. By the way, this is going through the origin, so the y-intercept is also known to you. But you have the skills, no matter what the equation of this function looks like, no matter how twisted it appears, you know what to do to find the x and y-intercepts. You also know what to do to find this point, and this point, because these are all extrema, extreme values. They are points where the derivative is equal to 0 or where the derivative is undefined. So think about the skills you have right now. The power you have right now is pretty incredible. You know, if I just gave you those points, I can even do this. I give you those points and I say, go ahead and sketch the function. I don't know how successful you would be in coming up with what the function looks like. You probably would start drawing curves through there, but you wouldn't get it looking properly. And in order to get a proper looking graph, you'd have to explore the second derivative and asymptotes and some other things. And these are all things we're going to learn in this chapter. Okay, so the first example. Use the above three ideas to sketch the graph of this function without a graphing calculator. So how do we find a y-intercept? Let's do the y-intercept first. This is where we let x equal 0. You know, I really believe that everybody should be able to see that the y-intercept is 0 because every term has a 0 in it. But I'll write down my work. This works out to 0. So the y-intercept is 0. And I'm not sure if anybody's ever pointed this out to you or you've given it some thought. But whenever the y-intercept of a graph is 0, there is also an x-intercept of 0. I really should say y-intercept. So whenever the graph crosses through the y-axis at y equals 0, it must cross through the x-axis at x equals 0. Let's keep that in mind. By the way, I've written the y-intercept here, maybe not the best, most sophisticated way. I should probably give it as coordinates. Okay, what about the x-intercepts? The x-intercepts are found by letting y equal 0. So we have to solve this equation. And we solve this equation, because it's polynomial, by factoring. Just double check to make sure I've written the question down correctly. It looks fine. I can factor out an x and be left with 3x to the 4 minus 25x squared plus 60. Now this is a quadratic thing that's left over. I know it's not squared to the 1 and then a constant, but anytime you have an even exponent on the first term and half of that number for an exponent on the second term and no variable in the third term, that's quadratic. I would like everybody please to do a b squared minus 4ac calculation for me, and you can go ahead and type the result in the chat. Okay, I'll just wait for a couple other people to confirm. Okay, what does that tell us? If b squared minus 4ac is negative 95, it tells us that this thing, well, it tells us two things. Let's be very careful here. Since b squared minus 4ac is not a perfect square, then that quadratic thing is not factorable. But going even further, since b squared minus 4ac is negative, that thing has no zeros. So it's at this point in time we would say, what's the value of x that makes this factor 0? And you would say 0, which means there's an x-intercept at 0, which is at 0, 0. Well, we already knew that. But since there are no zeros for this, then x equals 0 is in fact the only value of x that gives us y equals 0. So there's only one x-intercept. It's at the origin as well. And that was a very, almost a depressing kind of result as we do all of that work and all we discover is this graph goes through the origin. But let's find the derivative now. I'll go to a new page. Not interested. I'm just going to go to a new page so that I have a bit more room to do this. So I'm going to determine the derivative of that function. Again, you know me, I don't like the f prime thing. I'm going to write dy dx equals 5x cubed minus 75x squared plus 60. And again, when you do this, you probably just go on autopilot and end up making a mistake like I just did. Double check it. It's 15x to the 4 minus 75x squared plus 60. Are we okay with the first derivative? Any questions with that? Okay, we can factor out a 15 and have x to the 4 minus 5x squared plus 4. I can factor the middle part as a quadratic, the leftover part as a quadratic. I don't think we need to have a discussion about the discriminant here because we know it's quadratic, even exponent. Half of that and then no exponent for x on the last term, we don't need to use the discriminant because there are two numbers that multiply to give 4 and add to give -1, or -5. So it's x squared minus 1, x squared minus 4. That all factors further into 15, x plus 1, x minus 1, x plus 2, x minus 2. Any questions with that series of two steps that you're looking at on the board right now? Okay, so what are our critical values of x? Our critical values of x are plus or minus 1, plus or minus 2, which means that you have to do a first derivative chart. Now this polynomial is defined, the original function is defined from -infinity to infinity. And we're going to slice that domain of all real numbers using the knife in 4 places to get 5 intervals. So this is going to be a beast of a first derivative chart. Across the top, we can put all of our factors. I guess I'll rewrite them. I was going to just be lazy and just look at what I have here already, but I will rewrite it. X plus 1, x minus 1, x plus 2, x minus 2, a column for the derivative, a column for what the function is doing. And over here, -infinity to -2, -2 to -1, -1 to 1, 1 to 2, and 2 to infinity. So a couple of comments here. You've got a lot of things to fill in. You have to fill in 20 different signs in this chart. 5 intervals for, I'm going to throw the 15 in with the x plus 1, 5 intervals for x minus 1, 5 for x plus 2, 5 for x minus 2, and then you're going to have to complete the chart. So I'm going to give everybody a minute to fill those in, and then I will show you what I get. So try to fill them in on your own without looking at what I'm doing. Once you've done yours, take a look at mine and type whether you're in agreement or not. Now, the other comment I would make to you, we're not obviously not done yet. You need to be, accurate, slow enough that you're accurate, but pretty quick, because it turns out we're going to have to do the same thing with the second derivative. Because the second derivative is going to tell us eventually, not today, the second derivative is going to tell us something about the graph of a function. So now think about what you have to do. If I give you a function and I say graph it, you need to find the x-intercepts and the y-intercept. You need to find the first derivative to do a first derivative table. And then you're going to need to find the second derivative to do the second derivative table, and that's just to graph a single function. So you don't have to race through it, but you need to be fairly efficient. What are we going to get here? I'll use a different color. 4 negatives give a positive. 3 negatives give a negative. 2 give a positive. I don't know if you've ever thought about this, but if the number of negatives is odd, you're going to get a negative. If the number of negatives is even, you're going to get a positive. And then it's negative, and then it's positive. The function then is increasing, then decreasing, then increasing, then decreasing, then increasing. Hokey smokies. What that means is that at -2, there's a maximum because the function goes from increasing to decreasing. At -1, there's a minimum. At +1, there's a maximum. At +2, there's a minimum. Okay, so if I put everything together now in one view, what we know is that the x-intercept is equal to 0. The y-intercept is equal to 0. Collectively that means that the graph passes through 0, 0. There is a max at -2, some number. There's a min at -1, some number. There's another max at 1, some number, and there's another min at 2, some number. So I'm not looking at my first derivative table right now. I need you, a couple people, to let me know in chat if my memory is correct, that the max was at -2 and 1, and the mins were at -1 and 2. Okay. So we need to locate those points so we can sketch the function. That means you need to find y for all of those points, for -2, -1, 1, and 2. And y was 3x to the 5 minus 25x cubed plus 60x. And can I get somebody to let me know in chat if I wrote the function down correctly? Okay, so I'm going to do my calculations using my graphing calculator, but I am going to, and I want you as well, to resist the urge to look at the graph. Don't look at the graph. I will be giving you assignment questions and exam questions dealing with graphing that your graphing calculator will not be helpful in terms of seeing the graph. So we have to be able to be honest with ourselves here. I'm simply going to put in y and use my table to do these calculations. It's 3x to the 5 minus 25x cubed plus 60x. Double check my entry. There's 5 x's, 25 is negative, and there's 3 x's plus 60x. I'm going to change my table setup to be ask for the independent. Go to my table and enter in my numbers. I noticed something that will be important for the second little part of this lesson, and that's that there's some, we call it symmetry going on, that the y-coordinate of the first max and the y-coordinate of the last min are opposite to each other. So the y-coordinate at -2 is -16. The y-coordinate at -1 is -38. At 1, the y-coordinate is 38. And then at 2, it's 16. So what we are going to do is plot those points. I can't remember, did I give you a grid in your handout? Okay, and it's not actually a grid, it's just 2 lines. So we need some practice here in scaling things. I'll just put in my set of axes. The basic idea here is that horizontally speaking, you want to cover everything that's important horizontally. And what's important horizontally are the critical values of x. I'm not saying we're going to go from -2 here to -2 there. I don't think that's a good idea. I think I would go -1, -2, -3. And you're just doing this if you are a very type A personality. You might want to get out a ruler and measure things. I don't think it's necessary. You want to try to make it as accurate as possible, but it doesn't have to be perfect. So let's start putting in points. 0, 0 is a point of interest. Now, -2, -16. Look at the vertical aspect to this graph. It goes down to -38 and up to +38. So what I might suggest to you is 20, 40, 60. 20, 40, 60. So if you want to start labeling things, we can put a 2 here, we can put a -2 here, you can put a 20 here, a -20 there. But now I'm going to start plotting all of the points. So we have the origin as a point, -2, -16. This would be -10, -16 is approximately here. And keep in mind that that's a maximum. Then we also have at -1, -38, which is down. There's -40. -38 might be about there. And don't forget that that's a minimum. Then at 1, it goes up to 38. I don't know how obvious or apparent this will be to you, but I hope you understand, since the graph goes through -1, -38 and +1, +38, if we were to connect these 3 points, I'll just point at them. If you were to connect that point, this point and this point, they would form a straight line. It's just a point of interest for later. And then at +2, we're at 16. Which should be about here. Now we're going to do something else, which you could probably sketch the graph right now without doing this, but across the top of my diagram, I am going to put in a line. And I'm going to mark off on that line critical values of x. We had a critical value at -2. We had a critical value at -1. We had a critical value at 1. And we had a critical value at 2. And I want you to notice that these are the knife marks we made in the domain before. And I want you to look at your first derivative chart and tell me in chat what the function is doing in this first interval. What is the function doing in that interval? Going up, it's rising, it's going up, it's increasing. So what we do here, or what I do anyway, is above that line, I draw a whole bunch of arrows that are going up. What is the function doing in the second interval? Take a look at your first derivative chart and the interval from -2 to -1. What's the function doing? Going down. So in this interval, I'm going to draw arrows that are pointing downward. And then in the next interval, we discovered the function was going up everywhere. And then we discovered it was going down everywhere. And then we discovered it was going up everywhere. So this is a summary of the last column of your first derivative chart. And the reason that's important is when I'm drawing to connect these dots, I'm going to be referring to what's up top. The graph everywhere from -infinity to -2 is going up, and then down past it, which means the graph goes up, and that confirms that's a maximum. It goes down, but it must go up after -1. It continues to go up, then it goes down, and then at x equals 2, it goes up again. And if you were to use your graphing calculator, we can do that right now, actually, because it's in here. I'm going to change my window setting from -3 to 3, and I went from -60 to 60. Let's see how close it looks doing this. I'll go up in increments of 20. My old man used to say, that's not too shabby. That's pretty good when you compare what we came up with to what the thing actually looks like. When you study polynomial functions in Math 30-1, we graph everything based on multiplicities and zeros. But this only has one zero. So if all you knew was that it passed through the origin, without calculus, you'd be lost. Any questions with that example? All right, I haven't forgotten about my plan to decide on whether to move on to a second lesson or not, and what I have decided to do is the following. We're going to stop this lesson here. This lesson covers two main ideas, and on page 204 of your textbook, questions 1 and 2 are problems dealing with what we've just talked about. Finding intercepts is what question 1 is about, and finding intercepts along with the first derivative to sketch this curve. And that's where I'm going to stop the lesson right now. And I'm going to resume the lesson at, we'll say, about 2:20. And then we're going to cover the rest of this lesson. So all we're covering today is lesson 5.0, but we've broken it into 2 parts. So what I want you working on for the next 20 minutes is page 204, practicing your algebra skills with intercepts, and then doing a complete analysis of this function using a first derivative chart along with intercepts. At 2:20, we'll move on. I'm here, of course, the whole time, so if you have questions, let me know. And just let me know, was that first part of that lesson too drawn out, or was it just right, or was it too fast? It's all good. Okay. Thanks, always. Thank you for the feedback.